a project similar to what you have to do for your assessments. The assessments you have to do, assessment 2, 3 and 4, are not exactly the same as this. This is a lot harder. I've had to draw everything in from scratch. They'll be a bit easier to follow. But I just wanted to give you an idea how you would do it if you were given a plan. So you can see here what I've done is I've identified where the utility operator connection point is over here. We've had to put a high efficiency displacement unit in, a HED. We've also had to put in an 18,000 litre OSD. The size of that is 8 metres long by 1.5 metres wide by 1.5 metres deep. So essentially it's a reserve tank if everything backs up from the utility operator and we can't get the water out quick enough off the property, that'll allow us to use that as a reservoir that we can back it up into until we can get the water out. We have a silt arrestor as well to capture all the silt before it goes into the drains, where we can do our maintenance. And then a series of pits starting up here with SP1, Stormwater Pit 1, SP2, Stormwater Pit 2, and so on. What I've also done is I've broken the whole property into zones, as you can see, and worked out approximately how many square metres goes into each zone. For instance, SP1 is capturing approximately 20 square metres. All right. The roadway or the driveway is captured here by grade 3 up to this line here where this little dotted line goes across, and that's the zone going back into grade 3 and then coming this way as well. But anyway, we'll go into more of this in detail a little bit later. I just wanted to give you an overview of what we're starting with. So I've put this document together to give you an idea how to do this and where to look to find the information. So this is the Australian AS 3500, Book 3, the Stormwater Code. And from that, we're going to look at the design flow, the grade, and the pipe size. Now, the first place we have to look is how do we determine the actual design flows? And you'll see here, we select them from table 4.3, which I did earlier. You can go and do that if you wish, but in Australia it's a 5-minute duration that we've allowed for. And the other important things to note here, you will see, is the formula which we use in order to extrapolate out how many square metres are going into the stormwater drains. So you'll see here, so the design flow, Q, is in litres per second. And then we have this formula here, ECA, or sum of CA, equivalent impervious area of all upstream areas on the property in metres squared. Okay, impervious means it does not, if allowing for no water to go into the ground, it all runs off, that's impervious, like a roof for instance. However, a grassed area may be pervious, which means it's able to accept some of the runoff into the ground. But for the sake of our exercise, being in Palmerston and being in a high rainfall tropical climate, we're not going to allow for that. We're just going to allow for it to all come off the property. So the formula has two parts. We can either work it out using this part, which is quite long and drawn out, or we can take the easy option, which is ECA, which is the metres of the area. And we go back up here, we'll see here that catchment area there, or for instance this area on SP1 was 20 square metres. So there's 20 square metres would be the number that we would use for that particular calculation. So it would be 20 square metres and multiply that by the rainfall intensity for the area. So in Palmerston, I think you'll find when we go through and work it out, I think it's 232 millimetres per hour. So we multiply 20 by 232, and then we divide it by 3,600, and that will give us our design flow for the section of pipe. If I'll just flick this back around to the right for a second. The design flow for the piece of pipe running between Stormwater Pit 1 and Stormwater Pit 2. Okay, that gives us the design flow, and from that we're able to work out the size of the pipe and the grade of the pipe. So we'll come back to all of that. That's what I'm going to show you here now. So we'll rotate left, get this back to where we need it to be. So this formula will be important, and we'll come back to that later. Now the next point we're going to move on to is the design of the pipe drains. That's fairly straightforward as you read through that. I'll let you read through that in your own time. Incidentally, this document I have put over here in my learning area with the tutorials and PowerPoints. So if you go into tutorials and PowerPoints later and you want to read through this document, you can. I've just put together what's relevant for what you've got to do, and that's what this document is. Now the design procedure, 5.4.11.2, this is very important. We've got to determine the design flow in 5.4.8, which is what we just spoke about. Then what we've got to do is we've got to determine any physical observations, dimensions from the building plan, which that first drawing I showed you, we've done that. Then we need to select the pipe material and the Colebrook white roughness coefficient, and that will determine which graph we use in order to work out the hydraulic capacity for the size pipe we want and the design flow. Now if we look at this, it says if the hydraulic capacity is less than the design flow, assume DN pipe, then repeat the step. I'll go through that with you, but it says here until the hydraulic capacity exceeds the design flow. Well, the full pipe velocity shall not exceed 2 meters per second. That's great, except when we read the note underneath, which is very important, to reduce the possibility of overflow of stormwater pits due to increased energy losses, the full pipe velocity in the outlet pipe should not exceed 1.5 meters a second. So we've got to design the system so it doesn't exceed 1.5, and that's our safety margin when it comes to the pits. Okay, so there's our outline of how we actually do it, and now we're going to go into a little bit further. This is our Colebrook white roughness coefficient. Now for this drawing we're going to be using plastic pipe, all plastic pipe, so which is important. So and you'll see here all plastic pipe having a smooth, non-profiled internal bore. We've got to use the value for K is going to be 0.015. Okay, that doesn't mean a lot to you at the moment, but it will in a minute. What we're actually saying is this chart here, you can see how it's K equals 0.015. This chart here is the one we need to use for all plastics, copper alloy and stainless steel. I went through earlier and transferred the information off that table onto the charts. You'll see here if we were using fibre reinforced cement, it would be table B, which would be K equals 0.15. If we were using vitrified clay, precast concrete, cast iron, ductile iron or gal steel, we would have a coefficient of K equaling 0.6 millimeters. And if it was corrugated aluminium or steel, K would equal 3 millimeters in thickness. So we're not interested in those ones at the moment because it doesn't meet our requirements. Our requirement for this drawing is this chart here, which is chart A. All right, so that's how we select that chart, so that way we know we've got the right chart. So that's all of this information that was transferred down. Now, the minimum diameter. So, for single dwellings in rural areas, residential buildings on urban allotments with an area less than 1,000 square metres, the minimum diameter shall be 90 millimetres. So the smallest size pipe we're going to use is 90 millimetres. For other properties that are downstream of a stormwater inlet pit, minimum diameter shall be the greater of the diameter of the largest pipe entering the pit, or 150 millimetres. Okay, not going to worry about footpaths for this. Now, gradients. The minimum gradient of any site stormwater drain shall be given in Table 634. So note, no maximum gradient is specified, but designers should be aware of the possibility of scouring of pipes by rapid flows, particularly by sediment-laden water. Some stormwater can get pretty ugly and dirty and a lot of debris in it, so that's what that's all about. So a 90 millimetre pipe, the minimum gradient is 1 in 100. Same for 100 and 150. The minimum gradient in Australia is 1 in 100. For pipe size 225, 300 and 375, 225 is at 1:200. 300 millimetre pipe is 1:250. And 375 is 1:300. So that gives us our outline. So minimum gradients. It's very important. Okay, so let's go down here a little bit further. What I've also done is I've put together, I actually put it together, I printed it off from AS3500 Book 2, the Appendix C, which contains pipe grade conversion table. So it's in percentage and ratio. So that tells you how to work between the two, between the ratio and the percentage. What I've done on the left-hand side of the page is I've worked out how many millimetres per metre each one of these gradients works out to. So all of you should be familiar with 1 in 60, which is the minimum grade for our sanitary pipes. And we all know that for every metre it's 16.5 millimetres per metre. So for every metre we've got to allow 16.5 millimetres. That's where the 1.65% comes from. So and that's how we work it all out. So if the grade were 1 in 100, it would be 10 mil. If the grade were 1 in 160, it would be 6 millimetres. So that's all I've done. I've put that information there for you. For later on, when it comes to working out, you multiply how many metres there are by how much per metre, the fall per metre, and that's how much fall you have. And that way you can work out all your IL levels. So that's why I've put that there. So again, you're going to find this document over here and go to My Learning area, Overview of Learning, 1, Tutorials and PowerPoints, and you will find it in there under the Tutorial button. Okay, so here we go. We've got Palmerston Caravan Park. We've determined the ARI 20 years. The rainfall intensity there is 232 millimetres per hour. And we've used clause 545 and table E to identify what this rainfall intensity is for Palmerston. We've also used from the government website the soil for the Palmerston area, which is a sandy red Candesol. And there you can go to the website there and look that up, www.lrm.nt.gov.au. All right, and here we've noted that it's plastic pipe we're using. Okay, so we'll go back up now and see what we've got up here. So we've covered everything down here. So now we need to get into our example. And our example is going to begin here. So I'll just rotate this to the right. That's the same drawing we looked at earlier without any of the grades and zones indicated as to where all the water is going to run. So we've indicated all of that with that other drawing. But this clearly shows the pits, the stormwater pit 1, 2, 2, and then 3. 3 captures everything that goes into 2 and 1, as well as capturing its own load here, plus the load of grade 1 and SP4 and grade 2. So, and you'll see how we do all that in the charts. And then as we go through, SP5 captures the load of everything that goes into SP3, plus what goes into SP6 and what goes into downpipe 1, in addition to what it captures for itself, and that will be the loading that ends up going on this pipe here. Alright, so that's how we're going to do it. We're going to go through it. There's our scale. Now we start off with a sheet like this, which you would see. Now all I've done there is I've identified the sections of pipe. Each section of pipe has been identified. We've done that so we can work out what the maximum loading is on each piece of pipe. For instance, DP4 to SP12. If I go back here, there's DP4 right over here in this corner, and it goes back into that stormwater pit, SP12. Well, the only difference is we've accounted for it so we can work out what the loading is that's going to run through it. Okay, so that's what that is. So we've gone through and we've done all of that. So we've identified each section of pipe, and the easiest way to do it is to start at the top, SP1 to SP2, SP2 to SP3, grade 1 to SP4, SP4 to SP3, grade 2 to SP3, and that's how we've worked out. So each section of pipe has been labelled so that we can give it a size and a loading at a later stage. So that's what we've done, and that's what you're seeing there. Okay, I've just outlined here the whole boundary area that we're actually looking to capture. So it's fairly straightforward. And then this is where I've started to put the information in. So SP1 to SP2 was 20 square meters. SP2 to SP3 is the loading that went into SP2 plus the 20 meters for SP3. That's what gave us the cumulative total of 395. So there's 395 square meters of catchment going into that bit of pipe going from SP2 to SP3. So that's this piece of pipe here from SP2 to SP3. Alright, and that'll allow us to go in later. And so all I've done is I've gone through and I've worked it all out, what goes into this section here, this section here. You notice over here I've got a cumulative catchment for the 2 black dots there, because that's grade 1 going to SP4 and SP4 to SP3. So if I go back and have a look at that, that's grade 1 going right across here, catches this zone here. That all runs into SP4, and then everything, so that's one, that pipe there has a loading, and then everything that SP4 is capturing plus the loading from this one is what this pipe here takes all the way across into SP3. So we have to account for that. And we've done that by adding these two together. They're the catchments. And this is the loading of both catchments on that pipe. And that's what we've done. We've worked our way through all its pervious, what's come off the roofs. There's not much paved area there at this stage on what we've done. It's all driveway. As I said, I've allowed for it all to be the same, but it wouldn't matter. It would be the same. You can work out a variation to that later if you want to, but as I say, it's a tropical area, and in Palmerston the runoff is minimal. Now the other thing I've done, I've colour coded down the side here so I know which pipes go together. And see the orange, SP1 to SP2 and SP2 to SP3. That's how I know that that's where I put a cumulative total there. The same here with what goes into this one. It's just these two here, so that's what the black dots are. However, what ends up coming into SP3 to SP5, if we go there, SP3 is here, SP5 is here. The loading on this pipe here running between these two pits is everything with a green dot, right? All gets added together cumulatively, and that's what gives us a cumulative catchment there of 675 metres. And that's how we do it. All right, and then what we've got here is our pipe lengths. I've been through and I've measured all the pipe lengths, and you'll see there it's 14.5 metres from SP1 to SP2, 14.5 metres long. The only thing I've done is I've gone through and I've measured each section of pipe individually, which is what you would have to do. And that's where they are down on the right hand side there. So the only thing we don't have now is the design flow, the diameter, and the gradient. And all three of those things we're about to get here in a minute. And this is just another look at that same drawing again where I broke the zones off. You can see how the zones all flow to whichever pit the arrows go. And now I'm going to show you how you work out your design flow. So we'll rotate left for a minute. Now you'll see here we have our formula, and there it is there. I've put it there. So I always lay the formula out first. So it's how many square metres. So if we were to go back up, I might turn the thing at this stage, but it's SP1. We're working out what's going into SP1 in this instance. Okay, there's 20 square metres. We multiply that by the rainfall, which is 232 millimetres an hour, and we get 4,640. We then divide that by 3,600. That's what we're being told to do here. And that would give us a design flow of 1.29 litres per second. And if we go to the page here and we rotate to the right, you'll see here, got all those figures from the previous page, and you will see that SP1 to SP2, 20 square metres, is 1.29. And all we've done is we've gone through and worked it out what the design flow is for each section of pipe based on how many metres go into that pipe. So we'll go back, have another look, rotate left. We'll do another calculation, 88 square metres, 88 times the rainfall intensity for Palmerston, which is 232, times that together and you get 20,416, and then we have to divide that figure by 3,600 to end up with 5.67 litres a second. If it was 375 metres squared, we multiply it by 232, we get 87,000. We divide that by 3,600, we end up with 24.16 litres per second. And that's how we work out our design flow for each section of pipe. So it's fairly straightforward. So once we have that, we'll rotate to the right again. Once we have that, we just note it all in. And from there, we go to our chart. The chart we had previously, which is the one for plastic pipe. And from that, we're going to work out the pipe diameter, the maximum gradient at 1.5 metres a second. Okay, so we've got here 1.29. Now we come down here There's 1.29 is here somewhere. But so we'll go to 2. There's 2, 3, 4, 5. So 2, and that's hydraulic litres per second. So that's 2. So we'll work on 2. We'll go across. Okay, and down the bottom here we've got our minimum grades. All right. So 90 mil pipe. The minimum grade that we can get for 90 mil pipe, and we go up here, there's 2 there, so we go straight up. So where 90 goes below 1.5, because see, our litres per second is lower than where 90 goes through here, because we're at 1.2, so the minimum size pipe's 90, so we have to go up to 90. Where it's just below, right, we can't go to 1:40 because that's above 1.5. So we have to stay below 1.5. So the gradient, it's 90 mil pipe we're using, and the gradient's going to be 1:50. All right, so 30, 40, 50. There's 60. So if we go up, it's 90 mil pipe, and it will be 1:50. And if we go down here, you'll see there I've already marked it in. Say 90 mil pipe, 1:50. Now we just go through and we do each one of them like that. So if we go to the next size pipe, which is the one where we go from SP2 to SP3, we note that it's 395 meters because it's 375 plus the 20 that comes from SP1. So we add those two together. We did that earlier. It's 395. So we're saying it's 150 millimeter pipe at 1:90. So let's go have a look at that. So the design flow on that was 25.43. So there's 10, there's 20, 30, 40, 50. So 10, 20, it was 25.45, so that'll be 30. So we go up to 20, 30, there's 30 there. So we go across on 30 until we hit the yellow line, and then we go one below the yellow line. We could go on the yellow line, but we'll go below it. So go one below, it's 1:100. So the grade is 100, but the size pipe, it's greater than 150. Looking at this, I've got pipe is 150, so, and the grade is 1:90, so if you go up 1:90, yeah, there it is there. That's why I missed it. So there's 20, between 20 and 30, it's below it. There it is there, 150, because it's 25, so it's below it. So it works out there to be 1:90, which is what we have, and 150 mil pipe. We can see that there. All right. The next one is pretty straightforward. You can work your way through them from there. But I think you now know how to use this, because the design flow, these figures here are down the side. So 43, for instance, this one here, 43.5. You know, there's 50, 43.5. It's between the two. If in doubt, go up to 50. Go below the line. And you'll see we've just moved across to the next size pipe because it's above the 200. So we've got to keep going back across to the nearest pipe, which is 250. I've got my hand on it there. 250, and the grade is 1:200. That's this one here. So what have we got? 200, 1:200. So hopefully you can see how we did that. So you've got your design flow down the left and your grade in the right, and then when where the two meet, so long as it's below the 1.5 velocity or meters per second, that will give you the size of the pipe you need for that section. That's one of the hardest things to grasp with all of this, but once you get it, you'll be right. So, and that's how you fill out your list of what needs to be done. So there's mine for my drawing, and there's the final outcome. And you'll see here I've noted on the pipes, that's 90mm pipe, that's section SP1 to SP2 at 1:50. Remember, we can go back to that conversion chart to work out that 1:50 is equivalent to, I'm not sure, I can't remember now. 1:50 is, just buzzing back up here, rotate to the left, 1:50 is 20 millimeters per meter. So however many meters, multiply it by 20 mil. And that's how we work it out, guys. That's how you actually, then from all of that, you can work out your invert levels and everything else that you're going to need in order to complete your tasks. Alright, I hope you found that's helpful. I'll get this video up tonight so that you can have this to work on in the next few days. And that's the process. It doesn't matter what the drawing is, that's how we do it. So on that note, I'll leave you to it. Thank you.